Hello, seventh graders. So, by now you have taken the Chapter 7 test. I hope that that went well for you. If you remember, you did Chapter 8 earlier this year with Mrs. Drost. So now we're beginning Chapter 9, Section 9.1, which is about square roots. So before we talk about square roots, and I'm not exactly sure how much you've studied this, we're just going to start from the beginning. In order to know about square roots, it's important to know what perfect squares are. So perfect squares are derived by squaring a whole number. So 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared, and I should go back, I guess. You know a square of a number is just multiplied by itself. 8 times 8 is 64, 9 times 9 is 81, 10 squared is 100, 11 squared 121, and 12 squared 144. So here's a list of perfect squares that you should really memorize. And if they don't come easily to you, I would say write this list out on a card. It's going to help you in the future. So when we want to take the square root of a number, and this is the radical or the square root sign, the square root of 1 gets us back to this number here. So a square root undoes a square. So the square root of 4 would be 2. The square root of 9 is 3. The square root of 16 is 4. The square root of 25 is 5, and so on. I would encourage you to finish that list out in your notes. So we have something called a principal square root. If I asked you what is the square root of 9, you would say 3. That's the principal square root. And this will come in just a minute when we do equations using square roots. Okay, so what happens when we want to take the square root of a number that is not a perfect square? Here are perfect squares. So what if we wanted to take the square root of a number that's, let's say, between 36 and 49? Well, what happens is we get a number that is not a whole number, and those numbers are called irrational numbers. So irrational numbers have a decimal expression that goes on forever and never repeats. So an irrational number has a decimal that goes on forever and never repeats. So we had defined rational numbers before as numbers that can be written as a fraction. So irrational numbers cannot be written as a fraction. They have a decimal expression that goes on forever and never repeats. So let's take a look at an example. The square root of 51. So the square root of 51 would fall between the square root of 49 and the square root of 64. So the square root of 51 would be between 7 and 8. Does that make sense to you? This is something as a mathematician that you should be able to approximate. The square root of 51 is going to be between 7 and 8 because 7 squared is 49 and 8 squared is 64. And in fact, you should be able to tell me, using some logic, is this number closer to 7 or closer to 8? What do you think? Well, 51 is closer to 49, so therefore the square root of 51 would be closer to 7 than it is to 8. Now, if we wanted to find an approximation for the square root of 51, on our calculator, you can see right above the x squared key is the square root. So we have to access that by second. Now, turn it on first. Second, we have the radical, 51, and then we can press enter, and we see it's approximately equal to 7.141428429. And we know as mathematicians that that decimal expression goes on forever, and we never have a repeat. Now it's interesting, we have a 1414, but notice that it does not repeat like 0.3 repeating or 0.6 repeating. All right. Now, if we wanted to approximate the square root of 125, which two whole numbers do you think this number is between? Without a calculator, which two whole numbers is the square root of 125 between? I'll give you a minute, and you can pause if you like. But since 125 comes between 121 and 144, we know that the square root of 125 would be between 11 and 12. So this would be less than 12, but greater than 11. And we also know that it's probably going to be closer to 11 because 125 is very close to 121. All right. So now we're going to venture into the order of operations involving square roots. So we know the order of operations, PEMDAS, please excuse my dear Aunt Sally, or parentheses, exponents, multiply and divide, add and subtract. If we wanted to evaluate this expression, given A is 11 and B is 5, this is how we do it. We have 2 square root 11 plus 5 squared. The 2 right next to the radical means multiply. We just don't put the multiply there, but that's in fact what it means. The radical sign is a lot like parentheses. We have to figure out what the value is inside this radical first. So inside this radical, we would do this exponent. 5 squared is 25. Add 11. So we have the square root of 36 and our 2. And then if we can evaluate the square root of 36, which we can see up here, the square root of 36 would be 6. So this is simply 2 times 6, or 12. The order of operations. Okay, now I'm going to talk about something that is a very common mistake. A very common mistake. So first I'm going to ask you, what do you think? Do you think that the square root of a squared plus b squared is equal to a plus b? Now maybe I gave it away by telling you that this is a very common mistake. But let's take a look at this. Seems like it should, right? But the fact of the matter is, since we have this plus here separating these two terms, this is not true. This is not true. And to understand why it's not true, you could just choose any two numbers to test it out. Let's let A be 2 and B be 5, just for fun. So if we substituted those values in, 2 squared plus 5 squared, remember how we solved this with the order of operations, we'd have to square 2, which is 4, and square 5, which is 25. 4 plus 25 is the square root of 29. Meanwhile, over here, is this equal to a plus b, 2 plus 5? 2 plus 5 is 7. Is the square root of 29 equal to 7? That's not even close, is it? The square root of 29 is going to be somewhere between 5 and 6. So we can see if it's not true for any two numbers, then we know that this is not true. To disprove something, we only need one example to disprove it. This is something that we're going to see in the Pythagorean theorem. If you've had that before, it's a very common mistake that math students often do. All right, let's move on. We want to begin to solve radical equations. So note, the square root of x squared is just x. The square root and the square are inverse operations and they undo each other. Just like if we multiplied by 3 and divided by 3. Those operations, multiply and divide, would undo each other and we just have the number. Or a number plus 7 minus 7 is just the number. So if you are given, evaluate the square root of 3 squared, you can say this is a square root of 9, but why? Why do that operation? Just say that's going to be 3, right? The square and the radical undo each other. All right, we're going to use this property to solve equations involving square roots. So if we have x squared is equal to 9, we want to solve for x, so we're going to undo that square. So how do we undo the square? When solving an equation and the square root is taken, not yet, sorry. I'm going to square root both sides. The square root of x squared is x, and the square root of 9 is 3. I just told you that back here when I said the principal square root, the square root of 9 is 3. But now we've got a little detail. Since we were solving this equation, when you're solving an equation and the square root is taken on both sides, you must add the plus or minus sign in front of your answer. So we must say that x can be positive 3 or negative 3. Now why is that? Well, let's go back to the original equation. What number squared gives you 9? Well, of course, 3 times 3 is 9, but also negative 3 times negative 3 is also a positive 9. So when we're solving an equation, we're going to have two answers, plus or minus. All right. Still, if I said, what is the square root of 9, you'd say 3. That's the principal square root. But in an equation, you must put the plus or minus in front of it. All right, here's a little bit more complicated equation. And sorry, I wrote this down kind of wonky. The equation is 20 plus 4x squared is equal to 400. 20 plus 4x squared equals 400. What we want to do is we want to isolate the variable first. All right, how do we isolate this variable? First, we undo anything that's added or subtracted. So we'd subtract the 20. And we have 4x squared is equal to 380. Then again, we want to get x squared by itself. So we would divide both sides by 4. And off the top of my head, I'm not sure what 380 divided by 4 is. That's 95. So we have x squared is equal to 95. Once you've isolated the x squared, now we can square root both sides. Square root of x squared, square root of 95, square root of x squared is x. Since the square root of 95 is not a whole number, we are just going to leave it as plus or minus the square root of 95. And you might wonder, why didn't I find the decimal for that? Well, as mathematicians, this number is more precise than 9 point something. If we were trying to find the length of a piece of board or some other measurement in real life, then we could always approximate this, you know, the squiggles. Take the square root of 95, square root of 95, which is 9.746. And then if you wanted to round it to 1 decimal place or 2 decimal places, you could do that. If we rounded this to 1 decimal place, it would be 9.7. So don't get too confused about when you leave it like this or when you round it off. Those instructions would be given. If it's not a real life problem, then we're just going to leave it like this. Now, when you go to check your answers in your book will have answers like this. But really in higher math, we leave them like under the radical. Here's one more example. 5x squared is equal to 25. We isolate the variable first. So we would do that by dividing both sides by 5. And then we would have x squared is equal to 5. And once you get here, take the square root of both sides. The square root of x squared is x. Since we're solving an equation, plus or minus the square root of 5. I'm not sure if you've seen these type of equations before. It's hard to teach you without getting your feedback. I hope you are all doing well. Looks like I had one more point. That's what I just said. Here's example 5 in your book. The distance that something falls is equal to 16t squared. Find the time when the distance is 272. In other words, how many seconds does it take for something to fall 272 feet? 16 happens to do with gravity, which is 32 feet per second. And we'll get into this equation a little bit more. But for now, you're just asked to solve this equation. So what would you do to both sides? I hope you said divide by 16. 272 divided by 16 is equal to 17. So we have t squared, I'm going to just flip these on you, is equal to 17. Now this is a real world problem. We want to know how many seconds. So if I said square root of 17 seconds, do you see how that's just a little wonky? We want to round off. So we're actually going to take the square root of the 17. So second square root. Do you ever use your answer button down here? I recommend it. Second answer, so it popped the 17 in here, equals, and if we had to round off to 1 decimal place, we would say t is approximately equal to 4.1, and then we label it seconds. So here's an example of when you would actually round off your radical. So that was a whole lot of information. Here is your homework. This is page 480. These problems, I want you to do this set here without your calculator. And I will write these on the web page. All right, take care.